Airplanes do not drop bombs when directly over the target. The plane's airspeed is imparted to the bomb, and it falls on a curved parabolic course similar to the second half of the arc of a ballistic missile. The Norden Bombsight takes rates, speeds, times, and distances and converts these into angles to compute the release point for the bomb. Two pieces of information must be obtained from experimental test data. The first is the time of fall. Gravity causes falling objects to accelerate at 32 feet per second, but upward wind resistance causes the bomb to reach a terminal velocity. The shape and size of each bomb determines this wind resistance and how long it takes to fall from a given altitude. Therefore, for each bomb type, altitude, and airspeed, the bombardier looks up in a table how to set the bomb sight up for this. The second piece of information relates to the fact that the airplane will always be ahead of the bomb by the time it strikes the target. The bomb is impeded by forward and upward wind resistance, so when it strikes the target, the airplane is ahead of it. The distance behind the airplane at the time of impact is called the trail, and it is also determined by testing data based on bomb type, airspeed, and altitude. It is also provided in a table. So by the time the bomb has struck the target, the airplane is out ahead of it. And the distance that the airplane is ahead of where the bomb strikes is called the trail, which is seen here in the orange. We can imagine a triangle with a vertical side representing the bombing altitude, as shown in the red here. If we take the ground speed times the time to fall, we know how far the airplane will travel at the time of impact. This is called the whole range, which is seen here in the blue. Again, time of fall times ground speed is how far the airplane will travel before the bomb strikes the ground, and that's called the whole range. If we subtract the trail from the whole range, we end up with the actual range, which is shown here in the green. Again, whole range minus the trail yields the actual range. This forms the base of a right triangle. Therefore, we have the bombing altitude forming the vertical side of the triangle, the actual range forming the base of the right triangle, and the hypotenuse now forms the drop angle, and the bomb sight computes this. There's a telescope focused on a mirror, and the mirror is run by a motor. By adjusting the speed of the motor to keep the mirror locked on the target, the bomb sight is able to use this rate to compute the ground speed, and using time of fall information can compute the whole range. Subtracting the trail from this yields the actual range, and the bomb sight can then use this information to calculate the drop angle. The sight angle is the visual angle on the target. And as the airplane moves towards the target, the sight angle becomes more vertical. When the sight angle matches the drop angle, an electrical contact is made between the indicators, and the bomb is released. Pilots know that when there is a crosswind, the airplane must be angled into the wind to fly a straight path. This is known as crabbing into the wind. Although when off course, an airplane can repeatedly be turned back into the wind to get back onto course, it will be repeatedly blown off unless a corrective angle into the wind is established. The Norden Bombsight has a turn knob which will allow the airplane to be turned into the wind, but it will be repeatedly blown off course unless a drift angle is established, and this is done by using the turn knob and the drift knob together. This is called killing the drift. At this point, the bomb sight is facing the target. The airplane is flying the correct path towards the target, but the airplane's nose is angled into the wind. Not only must the airplane be angled into the wind, it must be on a parallel path upwind of the target at the time of bomb release. This is because the bomb will be carried downwind by the crosswind. The distance upwind of this parallel pathway is called the cross trail. The cross trail is equal to the trail, which we have entered from the tables, times the sine of the drift angle which has been established into the wind. Therefore, setting the trail allows the bomb sight to adjust for both trail and cross trail once the drift angle is established. The bomb sight is mounted on a turntable to simulate turning of the aircraft. A small walking treadmill has an electric motor attached, and to this was placed a poster of a bomb run. Today we will simulate a bomb run following the lead group, which has already successfully dropped bombs on the target. The stabilizer and bomb sight gyros are turned on for 3 minutes prior to activating the remainder of the bomb sight. The bomb sight is linked to the autopilot by this linking system here, which goes to the directional panel and then to the autopilot. The pilot's directional indicator here is located in the pilot's cockpit, and this gives the pilot the direction to steer towards the target. During the early phases of the bomb run, the autopilot clutch is engaged. At this point, the stabilizer gyro is stabilizing the autopilot. As the sight head is adjusted left and right to keep on the target, it communicates this information with the pilot's directional indicator, telling the pilot which direction to turn, or feeding this information through the linkage to the autopilot. The bombardier can also fly the aircraft using the bombardier's turn knob. During the later phases of the bomb run, the autopilot clutch is disengaged and the bomb sight clutch is engaged. This, along with the torque motor, allows the stabilizer gyro to now stabilize the sight head. During this phase, as the bombardier flies towards the target, he steers the bomb sight towards the target, and this is communicated to the autopilot through the linkage. As you can see here, when the aircraft is turned, the sight head remains on target. The search knob here is used to locate the target. The turn and drift knobs are used to establish the drift correction to counteract crosswind. The bomb sight is now faced straight on to the target, and the aircraft is flying the correct course straight to the target, but the aircraft is angled into the wind. The bomb sight gyro is now uncaged, and this allows the leveling bubbles to level the gyroscope. This also moves the telescope so that it is now vertical to the ground. The disc speed drum, also known as the altitude knob, is set according to the tables to provide time of fall information. The trail is adjusted here. The rate knob is set based on calculations. This also sets the rate sector indicator. The telescope motor is turned on, and you can see it rotating here, and the drive clutch is engaged. Once this is done, the rate knob is used to adjust and fine-tune the telescope motor speed to keep the horizontal crosshairs located on the target. And this sets the drop angle. The displacement knob is used to put the crosshairs back on the target if they have drifted off. With the telescope drive clutch engaged, the search knob no longer works. The bombsight is armed. When the telescope sector indicator meets up with the rate sector indicator, an electrical contact is made, and the bombsight release mechanism releases the bomb.